It's like we have a lot of people online, so I think we can go ahead and start. Thanks for coming to this DGRAV webinar. This is going to be the last one of the semester, so we'll start again in the fall and think of people you might want to nominate for talks, or if you want to nominate yourself. And today for our last talk, we have Vaishak, Prasad and Sukanta, Bose. So the first talk will be a shorter 15-20 minute talk. We'll stop for just brief clarification questions, and then after the second talk, we will have time for more extensive questions. So with that, I'll hand it over to Sukanta, and thanks everyone for coming, and thanks for presenting.
Hello, everyone. So yes, I'm going to introduce this work that Vaishak Prasad, who is now a postdoctoral fellow at Penn State, was working with me as a PhD student at IUCAA. We have since moved away from IUCAA to Penn State and Washington State University. There's a set of works here which were also published in collaboration with Anshu Gupta, Badri Krishnan, and Eric Schnetter. So what we're trying to do here is ask the following question. I mean, are there ways of probing strong gravity physics in black hole mergers, basically near their horizons or at their horizons, through gravitational wave observations? And let's see if we can forward. Yeah. So the plan for the talk is we actually take our inspiration from black hole ring downs. And indeed, in a binary black hole merger, which begins with an inspiral phase, eventually you get a remnant black hole that rings down, and in the process, well, through all of those phases, emits gravitational waves to future null infinity represented by Scri plus in this Carter-Penrose diagram. And the question is if there are distortions on the horizons or the common horizon towards the end, in these various phases that are correlated in some form with observables at Scri plus that are imprinted in these gravitational waves. So I'm going to give a qualitative sketch for why we think, expecting such a correlation is not misplaced. And we are not the first people to come up with this idea. It was proposed earlier by various people, including in this work by Jaramillo, Redzola, and others. After motivating this expectation, I'll hand over to Vaishak, who will then actually use numerical relativity simulations to test if these correlations are present, and if so, in what form are they present, and are there ways in which we can test this in the future. Specifically, we'll obtain relations between a representation of the ingoing horizon for momentum flux and the gravitational wave strain that is radiated away to faraway observers. Do similar relations that we first find in the inspiral phase, which involves two horizons initially, right? Also exist in the post-merger phase once a common horizon has been formed. That was also addressed in Vaishak's thesis. And then finally, what are the other various characteristics? For example, in the form of mass spin multiple moments of these perturbed horizons that may get imprinted in correlations in these outgoing gravitational waves. We may or may not have time to reach this last point, but to those who are interested, all these works are now published. What I'm showing here is borrowed from this nice paper by Jaramillo et al. And Vaishak will give you more technical details involved in this Carter-Penrose diagram. But of course, we use a conformal factor to bring future and past null infinity into a finite region on the screen. We begin with this past time-like infinity in I minus. Initially, there may not be any radiation, but a burst of radiation may come in later from Scri minus, the past null infinity. And if there is enough energy in it eventually accumulated, then it can induce the formation and growth of a dynamical horizon. And dynamical horizon is more suitable for our work because we actually want to track how the horizon evolves. We need something more local than more global concepts like apparent horizon or the teleological concept of the event horizon. We will also use the Neyman-Penrose null tetrad involving vectors that are inspired by these advanced and retarded null coordinates v and u. But the one way to conceptualize this problem will be to think of any perturbing source for the horizon to be somewhere in the space-time that also is correlated with the gravitational waves that go out to Scribe plus. So in that sense, we expect certain features or characteristics of the horizon to be connected with information going out, classical information going out to Scribe plus. So a little more on the motivation. Of course, one may perhaps trace all of these back to Vishwesvarayya's pioneering work more than 50 years ago. This cartoon was not present in his paper there, but he made it himself later. But the idea is that, yeah, he studied the stability of Schwarzschild black holes. And we now, thanks to a huge body of work, know that the quasi-normal modes of a perturbed black hole horizon are connected with the gravitational strain, maybe represented through psi4 that goes to Scribe plus. Of course, with gravitational wave observations, we know that what it takes to be able to observe these characteristics is not a sneezing ant, but another big, massive black hole that spirals in and then eventually merges with your black hole of interest. People have actually also studied head-on collisions, for example, in this paper, in numerical simulations to get initial hints of such the presence of such correlations. Of course, this outgoing radiation, we expect it to carry away information about the black hole mass and spin. The final object is expected to be, again, a Kerr black hole. The no-hair conjecture would say that even the information you get about any mass or spin multiple moments out to infinity have to be characterized by the masses of spins of the black holes that spiral in. In fact, it is already known through past work that the geometric characteristics of the black hole horizon, for example, this shear, will be correlated with quantities like Bondi-like fluxes at Scribe plus. And to understand what single concept could bridge these near horizon and near Scribe plus constructs, we can appeal to the Wild tensor psi and psi4. Actually, Wild tensor, which connects, the shear at the horizon and psi4 at Scribe plus. And this idea holds for binaries, not just perturbed single black holes. And the Wild tensor, and we'll be dealing only with asymptotically flat vacuum spacetimes, which involve black holes, but also gravitational radiation. So the Wild tensor is then essentially the Riemann curvature tensor. And you can get interesting projections of it on various combinations of the Newman-Penrose null tetrad to get psi4, which is related to the double time derivative of the gravitational wave strain, but also ingoing fluxes at the horizon like psi2, which is a different projection of the Wild tensor. Here, T and R are the time-like and radial vectors of a tetrad, which also involve the angular coordinates theta and phi. But you can from them form a different null tetrad where you have L as the sum, a weighted sum of T and R, or N, a weighted difference of T and R, but also M and M conjugate as shown here. So M is complex here and is a combination of the angular coordinates theta and phi. So psi2 itself, I mentioned shear on the previous slide. The shear is related to psi2 through this equation, and that itself can be fleshed out in terms of derivatives of one of these null vectors L. And to see the connection between psi2, on the one hand, psi4, you can invoke the Bondi mass loss rate, which m dot is basically related to the time derivative of psi2. So how the rate at which the black hole mass is growing is related to this ingoing flux, and that psi2 can be related to psi4 through the Wild tensor. So that's the basic idea. Can we construct such a connection for black hole binaries? That's what Vaishak will talk at length on. Um, and 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 also therefore, eventually the post-merger remnants that form from those binary coalescences. Of course, one deviation that we'll have to deal with is that we are not talking about isolated horizons, but dynamical ones. And so we use them and track them in numerical simulations and also track quantities like the projections we talked about, the shear and psi4 in those spacetimes. Of course, in the numerical simulation, you cannot go out to Sky Plus. So you go to some finite extraction radius, which is still of the order of 100 times the mass, the ADM mass of the spacetime. And then from there, you can extrapolate to greater distances, like realistic distances at which observers would be placed. Um, so, and we actually did multiple numerical simulations to deduce robust expressions for the relation between shear and bond in news, and then found similar relations for also other phases of the binary black holes, um, um, but phenomenologically. This in some sense can be a trigger for further analytical work, perhaps more difficult work, where one can check whether these phenomenological relations actually can be understood more insightfully through analytical studies of these spacetimes. But how do you test any relation we may deduce? And that's a difficult proposition because we are looking at something that an observer basically, or who is stationed at or very close to the horizon. But realistically, perhaps you can think of maybe accretion disks, inner edge of the accretion disk that would have electromagnetic signals that are able to climb out of these strong deep potentials to faraway observers. But then you have to involve matter, which is a daunting prospect. But if you want to still continue with vacuum spacetimes, maybe gravitational waves can come to the rescue, or just any measurements you can make, for example, of the gravity of this growing dynamical horizon. And what I'm alluding to is that gravitationally, at least in principle, you can measure the growth of the black hole masses during the inspiral because of the ingoing flux from the orbit of the binary A into the horizons. So there are quite a few symbols here, but I would like you to focus on a couple of things. There is the stress energy momentum tensor TAB, which this equation, by the way, is taken from this nice living reviews by Vaishak and Badri Krishnan. This, I believe, represents basically matter energy momentum falling in through a horizon. And whereas the second integral involves the shear, which I introduced earlier. So that could be, for example, the gravitational wave flux. But also another quantity that is dependent on the mass, the spins, change in spins of the black holes. But if you're dealing with non-spinning black holes, which is the case for Vaishak's thesis, then this term gets dropped. And if there is no matter involved, then you notice that any mass growth in our black holes going from slice S1 to a future slice S2 is connected with this shear. So if we are able to measure this mass change at a faraway distance, that could then be sort of a test for whether test for what the shear may be at the horizon, and then connect that with the gravitational wave observation through psi4 at a faraway distance. Past work, I already mentioned Jaromíro's work here, along with Macedo, Moesto, and Rizzola in a couple of papers there, who first suggested geometrically that such correlations should exist. And then there was numerical work by Gupta, Krishnan, Nielsen, and Schnetter, who actually, this is a plot from their paper, who numerically obtained this behavior as a function of time as two black holes spiral in. And from these graphs, they anticipated such a correlation. And what Vaishak did in the papers I cited was to make this correlation more concrete by finding a universal characteristic among multiple correlations with varying mass ratios and so on. So before I hand over, maybe you can take a short break here for questions. Maybe there's something in the chat.
Yeah, well, we switch screen sharing. We can do some quick questions. We will save any in-depth questions for the very end. But yes,
Yeah, Abhay, so thanks for the comment. Yeah, that's right. So you're right. We don't have to deal with Site here, so we will be focusing only on the share. So perhaps that addresses your concern. The last slide in the integral, okay.
Yeah, that was a slide 4.
Yeah. Thanks. Thanks. Yeah, so that's a typo. But so the thing is that, yeah, we will compute the shear at the horizon and then correlate it with psi4 far away. Thanks. Okay, there was another question on this one.
Function in the related to like the moment of the measure is the mass distribution.
I think your mic was breaking up. Maybe you can type the question or after Vaishak's talk, you can ask it.
Yeah, the audio was choppy, but we can come back to that question if you can type it out. Any other questions or comments in the meantime?
I just had a quick comment. You sort of had an open question, which is the last point of your early slide, maybe 1 or 2. Such correlations. Yeah, the last point up here. So in fact, it is true that there is a correlation in the quasi-normal mode regime, in the future. There's a direct correlation between the rate of change of multiple moments on the horizon and the BMS charges associated with super translations, the
Yes.
supermomenta and the dual supermomenta. And this was work that was done with Neve Kera, and it is in the review paper that Badri and I, not the one that you mentioned, but the one we just put out last month or this month or last month. So there is actually such correlation, and we understand that very well. So it's quite nice that observables at infinity, namely the BMS supermomenta and their duals, the nut supermomenta, are related with multiple moments in the horizon very directly.
Yeah, I'm still reading through your February paper, but yeah, that's a good point. In fact, there is scope for work, and I don't think anybody has done this yet. So that's right. In some sense, what you're talking about also characterizes, say, post-merger remnants, right? But are these like first-order perturbations that they studied, Neve Kera et al.?
That's correct. So Neve and I have done the work which has to do with is a first order perturbation. But in that regime, it's not first order. I mean, we have very systematic framework in which we see that the dynamical horizon and scry, what is happening there is completely well described by first order perturbations in the quasi-normal regime. So we give the conditions. And in that linear regime, if you like, I mean, within numerical accuracy, all that you can see is just this. And within that numerical accuracy, there is a one-to-one correlation between the time evolution of supermomenta charges at infinity and the multiple moments on the horizon. So you're right, it is quasi-normal, but the statement is that there is a clean regime in which numerical relativity, full NR relativity, is extremely well approximated. In other words, within the resolution of numerical relativity, there is no distinction between the two.
That's a nice result. I look forward to reading it. So I guess I'm not fully read your paper yet, but thanks for
Sure.
that out. Should we go on to Vaishak's part?
Yes, I think so. And I think there is a question in the chat. You can either answer at the end or maybe just reply in chat.
Okay, I'll try to reply that on chat. So in the interest of time, I think I'm going to stop sharing and let Vaishak take over.
Thank you. All right, go ahead when you're ready. Thank you.
Okay, I hope you can see my screen.
Yes.
Okay. Yeah, thank you, Sukanta, for the nice introduction, and thank you all for coming. So I will now pick up from where we left off, namely with let me start with the bottom left plot on this slide. And what was sort of already known at this point is that if you consider a post-merger scenario, such as the one depicted here, then you could intuitively think that there is a nonlinear region, highly nonlinear region in the space-time, which sort of sources most of the gravitational radiation. A, a major portion of that escapes to infinity, and this is what we would detect in our detectors. And a small portion of it, nevertheless, goes inside towards the horizons of the black holes and is absorbed there. And because if you sort of postulate that there is a nonlinear region which sources most of the radiation, then you could think that the radiation which is absorbed at the horizon could be correlated with that at infinity due to the common source. So one of the major points that we wanted to sort of address is whether we could think of such correlations to exist in the inspiral phase, where the space-time is no longer perturbative, and where things can be nonlinear. And for that reason, we turn to numerical simulations. So why is it difficult, or why is it non-trivial to expect such correlations to exist? On the left-hand side, what you see is the finite difference mesh from an instant of time, a Cauchy slice from Einstein toolkit simulation. And you might be able to see successive mesh refinement levels embedded, nested. And as you get closer and closer to the black holes, you need finer and finer meshes to resolve the high curvature scales that are present. And that's because the curvatures are very high, close to the horizon, much different from what they are very far away from the system where we record gravitational radiation, where we receive gravitational radiation. If we now zoom into this portion, what you see in the middle plot is the shapes of the horizon, the coordinate shapes, at 2.6 m after the merger from a q equal to 0.6 simulation. This is slightly after the merger, but still you see that the shapes of the horizons are quite distorted. The colors represent the height from the equator. And what you see inside in orange are two individual horizons encapsulated by a common horizon, which is formed late into the spiral. And as you can see, they're quite distorted in geometry. They, of course, the whole system gives rise to gravitational radiation, which we receive. And although using various post-Newtonian and perturbative techniques, we can quite accurately now model the early inspiral portion of the gravitational waveform we receive, we still turn to numerical simulations to understand the highly nonlinear dynamical regime very close to the peak of the gravitational radiation. And in this work, what we attempted to do was to ascertain whether there are such correlations between the dynamical horizons in all three phases of binary black hole mergers, namely the individual horizons in the inspiral and the common horizon past the merger, and how physics at these regions are correlated with what we receive at infinity. So right at the start, I'm going to mention some of the main results from this thesis, and also what I would spend my time discussing in the rest of the talk. First of all, what we find is that the modes of the ingoing gravitational radiation at the dynamical horizons in full nonlinear GR are strongly correlated with the outgoing modes of the news that we receive at infinity in all three phases of binary black hole mergers, in spiral, merger, and ring down. And I will, of course, make it clear what we mean by strong correlations. Mostly, we mean that the phasing is very accurate between the gravitational radiation that is absorbed at the horizon and that which escapes to infinity. Secondly, we find that the ingoing gravitational radiation at each of the individual dynamical horizons in the inspiral phase has a familiar chirp-like behavior. Namely, they have increasing frequency and amplitude as the black holes get closer and closer. And thirdly, we find that the ingoing radiation at the common dynamical horizon shows a quasi-normal behavior, much like the quasi-normal modes that we receive at infinity. And this, I believe, was the first time one could show this from a numerical simulation of inspiraling black holes. And thirdly, in all three phases, we find that the ingoing radiation characterized by the shear encodes information about the parameters of the binary black hole system, and one could estimate them using the shear itself. Okay, so let's first discuss the two regions that we'd be interested in briefly. Firstly, we'll discuss physics at Scri+. So, and I will pay special attention to what is done to extract Psi4 and compute Psi4 in a numerical simulation. So as Sukanta already introduced you to the wild tensor, we choose a null tetrad in each region of space-time. This is a basis of four complex null vectors at each point. And then you can project the components of the wild tensor on this basis. And to give you a very brief idea of what these null tetrads look like, there are of course four vectors which form the null tetrad. And what you see in this slide is basically the outgoing null vector designated by the magenta colored line and the ingoing null vector in blue. And there are two orthogonal basis vectors in the orthogonal subspace, sort of, and they are space-like dimensions, but you can complexify these vectors and that can give you null vectors, sort of, in the usual Lorentzian inner product. And for a Schwarzschild black hole in retarded coordinates, you can construct these null vectors at any point of space-time. You're, of course, free to choose whatever directions you want within the gauge freedom available to designate the outgoing and ingoing null vectors. But there are reasons to choose particular conventions. For instance, we would like to have Psi1 and Psi3 to be 0, and that can be done in such nice stationary and static spacetimes. And you can, once you define these null vectors, you can, of course, write down the 4 metric itself in terms of these null vectors. And that is sort of the motivation on how these null tetrads are chosen in a numerical simulation. They are certainly not stationary or static, but we try to construct those null vectors which are very close to a Kerr spacetime at very far away regions. And that's called as a quasi-Kinnersley null tetrad. And we project this wild tensor Psi4 on these components. And to obtain the strain that we are familiar with from Psi4, we have to go through 2 time integrations. And what I would like to, of course, point out here is that, first of all, Psi4 is not a scalar, although it's called as a wild scalar. It's a component of a tensor. It's complex in nature and carries a spin weight. So if you were to choose or transform these null vectors, the components would rotate among themselves and give you a different Psi4. And they're also not gauge invariant. There is residual BMS degrees of freedom at Scri+. And of course, you can transform Psi4 with these residual degrees of freedom. And so, this will typically lead to mode mixing by a small percentage, which we can currently also take care of. So in post-processing, what we do is we compute Psi4 on large coordinate spheres because we are dealing with a 3+1 scenario and we don't have infinite computation resources. We cannot have infinity on a numerical grid. So we compute Psi4 on various extraction spheres, and then we extrapolate it to infinity using sort of post-Newtonian or perturbed Kerr formulae to give the waveform at Scri+, basically by correcting Psi4 at finite spheres to Psi4 at infinity, motivated with perturbation formulae. And then we also correct for center of mass drift because there could be artificial reflections from the boundaries of the space-time, which would lead to a drift of the center of mass, which would again lead to mode mixing. And one could also choose an appropriate BMS frame so that it matches with the frame that we do waveform modeling in, for instance. And finally, we cannot just simply integrate out Psi4 to give the strain. It turns out that due to numerical noise at very low frequencies, if you did that, you would have a slowly drifting away strain versus time instead of the nice strain that we see here on this plot. So this is handled by basically using a filter to remove low frequency noise before making the integration, doing the time integration in frequency domain. So once you do all of that, you of course get the wonderful radiation. This plot shows the magnitude of Psi4 on a very large, in the volume of a numerical space-time. And this is an edge-on sort of view. So you see this very less radiation on the orbital plane itself. And once you have that, you have information that's required at Psi4. I will now move on to discussing, what happens in the strong field regime, namely at the dynamical horizons. Okay, so the concept that we are most familiar with is that of event horizons. And they are basically defined for a Schwarzschild black hole, for instance, as this 45-degree line in the Penrose-Carter diagram. It's a null hypersurface. It's three-dimensional in nature. And because of the way it is defined, basically as a future boundary of the causal past of future null infinity. This is future null infinity, and you take the causal past and you locate the future boundary, you get this line. Because of the nature of the definition, it turns out, firstly, that mathematically you need a complete conformal infinity. If you were to remove points from here, then by definition, you cannot really locate the surface. So that seems odd. If you want to discuss surfaces of black holes, why would I be worried about some missing points at infinity? Secondly, these are also heavily teleological in nature. And what I mean by that, I'm going to take a moment to explain this, is that uh, the event horizon does not grow and respond to the local physics of the system. Namely, if you have gravitational radiation, let's take this scenario where you start with a Minkowski spacetime. This whole region is a Minkowski spacetime, including the red region, including this region. And this is flat. And then later, at some point of time, if you were to throw in the radiation from infinity, concentrating towards the center of the spacetime, then at some point of time, you would expect a black hole to grow as you concentrate sufficient amount of energy. And once a black hole grows, and I designate this by this line, this is a space-like hypersurface, which we will eventually call the dynamical horizon. And once a black hole grows and you turn off radiation and the system settles down to stationarity, this horizon will asymptote to an isolated horizon wherein it's not absorbing any radiation. And that will coincide with the notion of event horizon, of course. But if you trace the event horizon back in time, you realize that even in the flat region of space-time, where no dynamics had begun, you have an event horizon. So you might have heard this phrase that we might as well be sitting inside a room, inside a black hole, which would form into the future. And this clearly explains how teleological the concept of event horizons are. And although it is a useful global space-time concept to understand from what regions of space-time you can receive signals at infinity, it's not very useful in dynamical situations where you want to discuss dynamical processes, especially at black holes. And furthermore, it has also been shown that in dynamical scenarios, these event horizons can have sharp boundaries and creases, which is certainly what we like. And there's also no preferred way to foliate them. And in contrast, the dynamical horizons, which I depicted by the space-like hypersurfaces, they are quasi-local. They don't require any quantities outside of this hypersurface to define them. And they also respond to the local physics of the system, which I will explain in a later slide. You don't need any information from Scri+ to define them. So incomplete Scri+, if at all, does not matter. Mathematical convenience. And then they are also smooth. They evolve smoothly. They are shown to be stable. And they also come pre-equipped with certain class of foliations, namely those on which these surfaces can be considered to be marginally trapped, namely the expansion of the outgoing null normal, if you were to draw here, would be 0. And that is what is shown here. On the right-hand side, you see two portions. Let's concentrate on the bottom portion of this plot, where you have a dynamical situation. The tangent vector to this surface, which we call the dynamical horizon, is space-like, and it has two null normals. And later on, once the dynamic ceases, it asymptotes to an isolated horizon, where the normal would also become the tangent. And in this scenario, what we have is for each cross section, you can imagine this to be an intersection of this three-dimensional hypersurface, which with a Cauchy slice, as we would have in a numerical simulation. You can locate an instantaneous marginally trapped surface, which could be regarded as the instantaneous horizon of a black hole. And all this is, of course, explained in detail in the living review, and you can take a look at it. And to go into a little bit more detail before we go on to discussing results, as I mentioned, for isolated horizons, they are isolated, as the name suggests. There is no energy or radiation being absorbed, so we would expect the surface to be null. And on the surface, you can show that the expansion is 0. That's how it's defined. And the expansion of the outgoing null normal is 0, but the ingoing is negative. That's why it is trapped. And on the interior, you have the expansions of both of these as negative. And here Q tilde AB denotes the intrinsic 2 metric on these two-dimensional instantaneous surfaces called marginally trapped surfaces. And nabla is a gradient compatible with GAV. The topology is S2 cross R in this situation. And there are nice things that you can infer from just these definitions mostly, namely that you can show that the horizon area does not change with time. You can show that it is D-track. You can also show that the geometry is unique. Given certain set of numbers called the multipole moments, you can reconstruct the horizon geometry irrespective of what gauge you use to compute them. And also the quasi-local laws of black hole mechanics, the quasi-static laws, can also be re-derived in a much more robust fashion using only quantities available at the surface. And dynamical horizons, which will be the topic of this talk, are space-like in nature as opposed to the null isolated horizons that we discussed. They are also foliated by marginally trapped surfaces. And many of the laws of mechanics and dynamics, especially the laws of black hole thermodynamics, sort of, can be extended into full process laws, the integral which Sukanta showed in his slides. You can covariantly compute the amount of energy being absorbed by the horizons. And there are also some results on uniqueness, stability, but here in this talk, we'll focus on the physics of these dynamical horizons themselves. Okay, and just to give you a very quick idea of the conceptual contribution that dynamical horizons have, one of the simplest ones to explain, you can imagine a situation where you have two punctures. These are, for instance, a Brill-Lindquist initial data, frequently used to construct initial data for binary black hole simulations. And this is an instant of time. And these two throats represent the punctures that I mentioned. And the surfaces of these punctures could be the apparent horizons of the black holes. And if you were to look at the geometry of this solution, then you find that you have two sheets extending below, connected by these two throats, and you have a common sheet which sort of contains both of these punctures. And if you were to use the ADM formulae to compute the energy of this Cauchy slice, then you would find that it's not just the masses of the two black holes, as can be computed in this special scenario by doing the same ADM integrals on their each individual asymptotically flat ends. It actually contains a binding energy as well. So, however, this wasn't the case in this very special case. In general astrophysical situations, we won't have such nice symmetries as a Brill-Lindquist data has, and things will be dynamical, and we quickly lose this picture. And then you can ask, what do we actually mean by masses of black holes? And the way I like to think of this is that the most accurate meaning that one can associate to the masses of the two black holes, for instance, this is a plot from the first gravitational wave detection, and
I think we might have lost Vaishak. He said he was going to possibly have internet issues, so we can wait a second. Hopefully he'll rejoin. I don't know if Sukanta, you want to take a question maybe?
Yeah, okay, that should be 150914. I think that's another typo for this first event. But yeah, if there are questions.
I will just call Vaishak and tell him that he is off, because he might not realize that he is off.
Oh, thanks. Okay.
Because I have a question. This all seems very gaugey. I can do lots of BMS transformations. I can do lots of transformations in the bulk to make toroidal event horizons and all kinds of things. Does this just sort of say that we get lucky in the gauges that you happen to see these correlations, or
It is true. I mean, that's why we made that clarification early on that, yeah, we call them scalars, psi4, psi2, etc. But they do depend on choice of slice and the null tetrad. So yes, in some sense, perhaps, yeah, I think Vaishak would bring this up eventually in his slides.
Yeah.
Perhaps we got somewhat lucky that all we had to do was just slide the shear oscillations at the horizon with respect to the gravitational strain, but we didn't have to do any other scaling. So perhaps it was a fortuitous choice of a gauge, and that is also scope for future work. Yeah, how gauge restricted are these relations that we are finding? Is there any general characteristic to this?
Right. Okay. Thank you.
Okay.
It's like,
Vaishak,
yeah.
Sorry, yeah, that's the power fluctuation.
No problem. We took a question while you were away. So I think, I don't know when you saw you dropped out, but the plot of 5914, I think, is the last we saw on the call.
Right. Let me quickly scroll to that.
Yes, that's the last we saw.
Okay. Okay, so moving on to the next slide. So this sort of summarizes um, uh, what quantities specifically we have to use to study these correlations, and that is partly inspired by this by the flux laws at both at the horizon and at infinity. At some point of time in the project, I realized that if you look at the flux law at the dynamical horizons, then you have this relation that Sukanta brought up. And basically, it contains two terms. One is the shear, which encodes information about the transverse gravitation radiation being absorbed at the horizon. And you have another term coming from the spin aspect, which is, of course, zero if you have dark spinning black holes. And shear is defined in this manner, as you can see on the slide. They are basically projections of this matrix composed of the gradient of the outgoing null normal. Am I still audible?
yes.
Okay. Okay. And at infinity, you have analogous formulae that you can construct using the news of gravitation radiation, which is a single integral of the psi4. And then I realized at some point that the correct quantities to compare was actually the shear and the news of the shear at the dynamical horizon and the news of gravitation radiation at infinity. And in fact, in the Bondi-Sachs formalism, you can show that if you compute the shear of the ingoing null normal at infinity, that would give you the news of gravitation radiation. So that fits in quite well with that. And the blueprint is as follows: run numerical simulations, in this case, non-spinning varying mass ratio black holes, locate and track these marginally trapped surfaces, the apparent horizon through the simulation, two individual horizons in the inspiral and one common horizon in the post-merger. And then on one of these surfaces at every instant of time, compute the Newman-Penrose quantities at the dynamical horizons. And I already discussed how we prepare the waveforms at infinity. And the goal is to use data analysis motivated quantities to discuss correlations between the shear in the strong field regime and news at infinity. And here is a list of simulations that we ran. And these were, in fact, one of the first simulations to come out from India, I suppose. They all have zero spins, then they are varying mass ratios, and all the results I discuss in the next few slides hold equally well on each one of these simulations. And we also derive a phenomenological expression relating the shear and the news, which is fit across these simulations. Okay, so the details are in these two works. Please go ahead and take a look if you're interested. And basically now we have two dynamical horizons inspiraling in the inspiral phase, and then that leads to the formation of a common horizon later into the inspiral, which asymptotes to an isolated horizon of the remnant black hole. And we will now discuss the relationship between radiation being absorbed at the individual horizons and the common horizon and infinity. And here are the results. So for a Q equal to 0.25 scenario, what we show in this plot in blue is the news at infinity, and what is shown as dashed orange is the shear at the horizon itself. at one of the horizons. In this case, it's black hole 1, but there's also an equally nice looking plot for black hole 2. And what was perhaps surprising here is that all we had to do to get these to match well, as shown in this figure, is we had to take care of a time translation, which would roughly correspond to the extraction sphere on which the radiation was extracted prior to extrapolation to infinity. And we also had to just take care of a phase shift between the two waveforms. Although the physics, the horizon itself is causally disconnected from infinity, because remember, these horizons lie inside event horizons and nothing can escape the surface of horizons and reach infinity. Although that is the case, and although the curvatures are entirely different in the strong field and the weak field regime, we didn't have to do anything else apart from just a time shift and a phase shift. And of course, the amplitudes have been normalized appropriately. We didn't have to scale the time axis. And this is sort of a surprising result that we found. And this was found to be true equally well across the simulations that we have run. And the source of it, of course, we don't know. It could be the nice gauge conditions that we are using, or it could be something physical about the dynamical horizons themselves. And if you sort of use the shear at these horizons and treat them as signals and search for a best matching template constructed from one of the well-known approximants, then you find that the best matching template, which is shown as a blue square here, probably, I'm sorry if you can't see it, it's right here. The best matching template, and if you look at the parameters of that template, you find that you get back the parameters of the simulation. So the shear encodes information about the system itself. The same thing continues to the ring down. And on the right-hand side, you see the shear of the common dynamical horizon, the outer common dynamical horizon, immediately after it is formed, which is at this point t equal to 0, they'll be heavily deformed. And you can no longer, in fact, think of them as quasi-normal modes. But if you use the news at infinity and sort of do a similar thing as done on the left-hand side in the inspiral, you find excellent phase agreement between these two. Of course, I forgot to mention the inspiral that there is some amplitude disagreement as you get closer and closer to merger. And we are not fully sure why this could happen. This could be related to low finite differencing orders we are using to compute the shears themselves. And we are currently trying to improve this with spectral methods in SXS using SX simulations. And in the post-merger phase as well, you can do a similar thing as done here and find that you can recover the parameters of the remnant as well as the parent black holes using just the shear information available in the strong field regime. And we did various experiments. For instance, what I just described to you in the plot is listed here. We compute the match shown as a percentage here between the shear and the best matching template. And we also list the recovery parameters that we see here and the percentage errors that we get from it. And in the post-merger phase, we also do multiple checks. For instance, we fit them to quasi-normal modes, a single mode to start with, and we try to recover the quasi-normal frequencies, estimate the masses and spins. We also compute the spins through quasi-local methods to direct integration on the surfaces. And we find that in all these exercises, the information encoded in the shear could be used to estimate the parameters of the black hole. I think I'm running out of time, so I will just quickly flash this slide. You could inject the shear at the horizon into a detector with noise and do a full Bayesian parameter estimation, and you would roughly recover the masses and the spins of the remnant. And on the right-hand side is a plot showing the recovery of the spin of the remnant using 3 different methods: quasi-local in blue, remnant parameter estimation using a template bank, and just using quasi-normal fitting is shown in green. And they are all roughly in agreement. Perhaps the most useful and interesting product of this find is that we basically found that you could express the news at infinity as a linear combination of the shear of the individual horizons, alpha 1 and alpha 2 being constants for a given simulation, and them being complex constants, in fact, to take care of the phase. And you could, in this fashion, we also found that not only that you can relate the newses to the individual shears, but the individual shears are also related to each other. And this was in ansatz. We used the shear data across simulations, and we fit them to this power law, which was an ansatz, and we found this power law index to be minus 0.7. And using basically this and this, you could come up with an expression that relates the news of radiation at infinity to the shear at the horizon. So in fact, you don't have to even run a numerical simulations to compute the shear. Given the strain template or a waveform from your favorite waveform model, you can estimate the shear. It's not exact, of course, but you could estimate the shear and therefore the amount of radiation being absorbed by the black holes. A similar expression is also found to hold in the post-merger phase for the common dynamical horizon. And in this case, the ansatz which worked well turned out to be a polynomial, and we fit them across the simulations to get the coefficients of these polynomials. So there is such a phenomenological relation which could be used to compute the energy absorbed by the remnant black hole in the post-merger phase. So I will skip that. And these correlations, of course, continue mode by mode. One can show that you can decompose the shear as spin weight 2 spherical harmonics and study the correlation between modes. On the left-hand side, you see the shear at the horizon. On the right-hand side, you see the news at infinity. And this is also shown in this animation. So left-hand side is the news, right-hand side is a shear. This is sort of a top view, and you see the beautiful quadrupolar, dominant quadrupolar pattern. And the phasing is also in agreement with the motion of the black holes, as one would expect. And that is shown more clearly here. These are two individual horizons in spiral phase. And if I freeze this at an instant of time, if you draw a line between the two black holes, you also notice that there is a small phase lag between the orbital phasing and the shear itself, in agreement with the intuitive expectation of finite travel time for the influence of one black hole on the other. Okay, so this is sort of my last slide, last slide, yeah. And the takeaway picture from this whole set of results that we found is that in the in-spiral phase, as the two black holes get closer and closer, they impart influence on each other, and they deform the horizons, and the amount of radiation being absorbed by them increases as the two black holes close in. And the counterpart of the radiation that we receive at infinity is basically encoded in the shear, and that also has a very similar multipolar structure to that of the radiation we receive at infinity. And as the black holes deform, and then leading to a formation of a common horizon which encapsulates these two, one can show that these deformations are sort of transferred to the post-merger portion. And then in the rest of the dynamics that happens in the post-merger phase, the common horizon of the final black hole absorbs gravitational radiation complementary to the deformations that it has, and approaches equilibrium to an isolated horizon late in time. And throughout these phases, you have these correlations. And tidal deformations of black holes for another day. And this is my last slide. So the takeaway message and the things that we have been thinking about on how to use these results is that, of course, shear forms an important part of the tidal coupling in the strong field regime. And currently, our waveform models don't exactly take into account the absorption of radiation at the horizon itself. So these results could possibly be used to model these radiation effects and include them and improve our waveform models. We also would like to study the gauge sensitivity of these results. We did not find any sensitivity across these simulations. Like I mentioned, we didn't have to do any transformation of the time axes at the two surfaces, but we would like to study this in more general class of gauges. So I'm currently looking at simulations from SXS and using the generalized harmonic gauge to study and find out if these correlations do exist there as well. And the hope is to somehow try and figure out a way to do tests of GR in the strong field regime, because these correlations could possibly give us a direct route to sort of understanding the strong field dynamics of black holes. And I'm also exploring ways to speed up numerical simulations of speed up horizon finding using these relations, because we approximately know what the shape of these horizons should be through these phenomenological relations. There is also a motivation coming from the tidal deformation work that we did, and that which I could not explain here. Sorry for that. Maybe for another time. And of course, what I should say is that we do not have an analytical connection between the source and the field multipole moments, or the radiative modes of the shear at the horizon and the radiative modes of news at infinity. These relations are phenomenological at the level of correlations, and it would be nice to have a theoretical sort of aspect of this. And I think this is where I would stop. Be happy to take questions.
Thank you both. Do we have any questions? You can put your hand up or put something in the chat.
Yeah, I'd like to ask a question. When you showed that surprising agreement in the in-spiral phase between the shear on the horizon and stuff, I was wondering, the dynamical horizon's a space-like surface. So what time are you using to talk about when you're comparing with the time variation at infinity?
Yeah, thanks for the question. That's a good one. So, well, the time we are using is basically the time coordinate of the Cauchy slice. So this can be related to the time coordinate at infinity, where waves are extracted by a simple time shift. So if you like, they are the inertial coordinates of the space-time at very far away regions.
But these are sort of not perturbative, right? These are full, dynamical things.
True.
Connecting the surface at infinity to the black hole seems very arbitrary.
That's true. And this is something that we still have to sort of understand. We didn't have to do anything much other than basic time translation and phase maximization to get this agreement. And you're right in saying that these are very different surfaces, and these relations seem to hold in nonlinear regimes as well, very close to merger. The red line here is the merger, in fact. Yeah, thanks for the question.
Leo has a hand up.
Hey, nice talk. And this is kind of continuing along the same lines, but I just wanted to verify that the choice of coordinate, not in the bulk, but at scry, is the retarded time, which is defined in terms of like u equals t minus r to agree with like the origin of coordinates in the Cauchy system. Is that right?
Yes, yeah.
Okay.
Yeah, that's right.
All right. Yeah, I mean, I think it's not extremely surprising because the light crossing time of this binary is only a few tens of ems, which is small compared to like the orbital time scale that you see there in the graph. So maybe it shouldn't be super surprising that these things that like just the Cauchy coordinate, the Cauchy time coordinate, and that choice of retarded time on scry give you this approximate agreement.
I see. Okay, I haven't thought about it that way. Thanks for the comment.
I think Steve had his hand up next.
Yes, I was intrigued by your comment that one might be able to probe, for example, modifications like compact objects merging as opposed to black holes. But one comment, correlation is not causation. In fact, this plot is sort of a reminder of that. It seems to me, I don't know if this is the explanation, but one could be deforming the internal objects inside the bigger horizon through the common dynamics of the space-time. So that doesn't mean information from those is escaping to infinity. It's just that whatever is, the common dynamics is deforming those in a way that's correlated. But anyway, I'd be interested in your comments.
Yeah, this is spot on. So this is exactly what I meant when I said that the dynamical horizons lie inside these event horizons and they are causally disconnected from observations. But the sort of at least in the post-merger phase, we do have a sort of an idea of how this could happen. This is what I explained right in the beginning. If you think intuitively that there's a common source, a nonlinear region from which most of these waves are generated, then because of this common source, you have a part of the radiation going in, part of the radiation going out. And although these surfaces are causally disconnected from Scribe plus, there seems to be some correlation. In the in-spiral, I don't have any such picture, but the general expectation is that if the physics at the horizons is different, then probably the details of the nonlinear dynamics, nonlinear region which gives rise to these waves in the first place would be different. And therefore, such a modification in the strong field regime would indirectly have an effect on what we receive at infinity. This is roughly what we sort of think.
Yeah, so an interesting idea, but that seems like that is maybe making the leap from correlation to causation. Is
No,
that a fair way to say it?
Yeah, we are not implying causation at all.
Well, I think if there were some different dynamics of the things inside the common horizon, for that dynamics to be manifest in the outside signal, that would, that is, well, requires something like causal propagation of that information out.
Yeah, so we're not implying.
These correlations need not hold for a modified theory of gravity. These are the results we find for GR, for instance. And we don't imply causation. Yeah, of course.
No, there is no causation. What could be happening even in the in-spiral phase is that, of course, the time-varying quadrupole moment is the dominant source for the gravitational radiation that goes away from this binary to Scribe plus. But both black holes may also be absorbing some radiation at the cost of affecting the orbital evolution. That response of the horizon to this influx is correlated to the radiation going out to Scribe plus, but again, from the orbital dynamics. It's not that anything is coming out of the horizons and leaking out to Scribe plus. I don't know if that clarifies your concern, Steve.
I think that helps. Let me think about it. Thank you.
I think next question is from Keith.
Oh, I just had the same question as Steve. I don't particularly see how you could really use this to probe the strong regime, but I don't need to say any more. I'll let Abhay ask a question.
Yeah, no, I think actually I was going to just comment a little bit about Steve and the question that Keith was going to ask, but did not ask. Yeah, so basically this, the general thing is that at least in this remnant part, at late time part, which is showed with the in this diagram, right, with these arrows going inside, and there's a green blob outside. So the general idea is that the green blob outside is really the top of the potential, and from simulations it does look like a lot of, and at late times, the lot of radiation is really sloshing around near in this potential well, if you like, just outside the horizon. It's outside the horizon, outside the event horizon. And then some of it falls in, and actually the one that falls in seems to be responsible for, surprisingly, ironing out the multiple moments. In the initial part, the multiple moments structure is very, very complicated. It is actually time evolving, but that irons it out, and then things go out to infinity. So somehow both these things are coming in that pool of radiation near the top of the potential well, and that I think somehow is responsible for correlation. So if you like, it is not causation in the sense that a causal signal is going from something to something, but rather it is really, you've got the same object, same reservoir from which both of them are coming. And in that sense, there is this correlation. And just going back to Gary's question just for a second, I think Leo actually basically answered it. So and the dynamical horizon does come with a natural slicing, and therefore there is actually a time function up to, of course, the function of that time itself. But then if you actually look at the retarded times, then going to scry, I think this is all heuristic. If I look at the retarded times going from scry, from these marginally trapped surfaces of the dynamical horizon, then you can actually match what is happening out at infinity with what is happening at the horizon, in the sense that you can eliminate the time rescaling freedom by just considering the retarded time. So heuristically, that is what is happening. But I still have one thing, something that I don't understand, which is really that what was being plotted here was really referred to as particular theta and phi, particular angular direction on the individual horizons and in the and at scry. And now how they are correlated is not so clear to me. So perhaps they're also correlated just by this retarded, null rays which are going out, so to say, along the. But the point is that there are two different things on the two different horizons. I get choosing some angles on two different individual horizons, and somehow that is correlated with something to the news at infinity, which is happening at a certain fixed angle. So how three angles are correlated is not clear to me at all. I mean, conceptually clear to me. So maybe Vaishak can or Sukanta can say something.
Yeah, thanks for the comments. So I mean, the general picture here is that because in hindsight, because the full modes, I think I showed that here, the full function, the shear on the horizon themselves are correlated, and what we show in that plot, I may have missed it. If I have, sorry about that. So we basically pick out one point very close to the pole, and we also pick, because they are not spinning simulation, the orbital plane is not precessing, we pick a counterpoint very close to the news, very close to the pole at very large spheres. We alternatively also just use a 2,2 mode of the news because it is the dominant one, and then we correlate these two. And in hindsight, because the full distributions are correlated, or they're correlated mode by mode, if you like, you could probably understand these correlations also happened on a point-by-point basis, up to a phase shift, which is taken care of here.
So you're saying that there is a diffeomorphism somehow from the two-sphere, the black hole horizon, and the two-sphere at infinity, such that the two are mapped to each other. And what we are trying to understand is the nature of that diffeomorphism. Visually, they look similar, but that just may be because you're just looking at 2-2 mode, and so the 2-2 mode has the same quadrupolar behavior. So there's not deep fact about that, right? I mean,
right.
You happen to be looking at 2-2 mode, so okay, thank you.
We are past the hour now. Niels, you can ask your question if Sukanta and Vaishak want to stick around, but if anyone needs to leave, let me just remind you that this is the last DGRAV webinar of the semester, and we'll see you all again in the fall. But if Sukanta and Vaishak are still available, Niels, you can go ahead and ask your question.
Yeah, I guess I'm still, my concern is still that this is all very gaugey, right? Like, when we run CCE on our waveforms in SXS, the BMS freedom gives us a waveform that if you showed it to anybody, they would be like, that's utter garbage. And you have to do a BMS frame fixing on it. So I'm not at all convinced that it's more than we once again got stupidly lucky that the gauge choices in NR happen to give us something that looks like what we expect. Mm-hmm. Because you can also do gauge choices and get toroidal event horizons and these kinds of things, and so I'm not sure how that I don't expect that this would hold for an essentially infinite class of gauge transformations.
Mm-hmm. Yeah, I mean, in one sense, this is what we thought. This is what we used to think, at least. And it's still not ruled out, of course. But there are some results, some works that discuss for instance, do a reslicing of these dynamical horizons and try and study quantities like the variation of the area or the masses and so forth. And what is known is that as long as you keep away from very extreme choices of gauge, which would be probably unintuitive or non-physical, you would get very, very small variation of the masses across the different gauge choices. But this is very, hand wavy, of course. And what I'm sort of interested in trying to do now is to study precisely this point, study it in generalized harmonic gauge, for instance, using SXS.
Yeah, yeah, I think the GH gauge also ends up being very nice because it's sort of designed to make the space-time as boring as possible, right?
Yeah.
Like the choices are literally drive the lapse to 1 and drive the determinant of the spatial metric to 1 to make it as boring as possible.
Yeah, I agree. Yeah. Probably I'd like to also think of some extreme choices of gauge.
Would it be easier to change the gauge in the waveform, where once you have the waveform, you just do BMS transformations on it and you don't have to rerun the NR simulation?
Right.
I don't know if that would, I mean, it's not quite the same thing, but might.
Yeah. One could think of that. Yeah, that's certainly a way forward.
Just thinking about trying to minimize how difficult it is to do. And then I guess as you go infinitely back, do you expect, like on this one, do you expect the amplitude of the shear to keep decreasing? Or, I mean, that it doesn't, explode like it does in the merger case for the strain. I'm like less surprised by that.
Yes, so we looking at the value, the magnitude of the shear itself for simulations that start farther and farther apart, we found that the shear does decrease as expected. And for an isolated horizon, it should be 0. And as you can see on the right-hand side, up to a numerical noise, it falls by about 2 orders of magnitude, but probably we can regard this as 0, as should be on an isolated horizon.
Yeah, I mean, with spec, you might be able to do
better
to get that, to 6 orders of magnitude or something like that. But yeah, okay, cool. Thank you.
Yeah, if I can add something else, yeah, I mean, to address the gauge question, maybe a somewhat less complicated place might be to look at what happens just before we get into the linear perturbation, QNM regime, right? There also we have a phenological relation between the news and the shear, but maybe because it's basically almost an isolated horizon, perhaps we have better control on the choices.
Yeah.
Yeah, I'm just
right. Yeah, it's hard, right? Yeah. I don't know.
Could I just one say, Neil, these are fantastic questions, but are you saying mainly concerned more about the 2 individual black holes and their correlation on the correlation of the shear on the 2 individual horizons with that infinity? Is that what your focus was, or was it about the remnant?
I mean, I think the remnant is better understood.
Right. Okay.
But
so as far as the individual black holes are concerned, the state, I mean, it was really reflected in your questions already, but basically one can actually introduce gauge invariant multiple moments, right? So there's a coordinate system that you can introduce in theta phi directions, if you like, or YLMs you can introduce in theta phi directions. And then using those YLMs, you can just do the mode decomposition of shear. And you can, and that is kind of gauge invariant because in the asymptotic past, both of them are going to occur, right? So asymptotically in the past, they're both going to be axisymmetric to an excellent approximation. And there you can, and then there's a procedure of dragging those YLMs defined in the asymptotic region to the region where the horizons are distorted. And this was the gauge invariant procedure that some time ago Miguel Campaglia and Shah and I had given, and that is used actually in this SXS evaluations of the multiple moments. So I think one can do that, and therefore one can actually do the mode decomposition of the shear in this invariant manner, and you can do similarly the mode decomposition of the shear in an invariant manner at of news at invariant manner at infinity. So I think one there's a, in other words, for me,
No,
these
but the
results are
waveform is
intriguing,
not
and they
gauge
say
invariant, period. I don't understand what you mean. I cannot do anything with the news that's gauge invariant because the news itself is not gauge invariant, right?
What do you use non gauge invariant?
I can do a BMS transformation on the news, and that's like,
yeah,
that's a different gauge.
Right. So the statement is that the news tensor is gauge invariant.
Okay.
So maybe we should talk about this.
Yeah. Okay.
Because I don't want to take too much time here. I think Meg is getting impatient to finish the thing. It's already 16 minutes.
No, sorry.
Past. Yeah, I'm very happy to discuss this in detail.
Yeah, I think we're probably going to have to come to a close soon, but thanks again for great talks. Obviously very interesting conversation. So hopefully you all can finish up offline. I think that's it. Unless there's any last minute, very quick questions. Thank you again so much. That was great. And see you all at the next webinar in the fall. Bye.
Thank you so much.
Thank you everyone for the questions and comments.